Okay, hello and welcome to Recitation 12. We are once again going with a recorded recitation because you just had your midterm on Thursday and we are grading your midterm during normal recitation time. So yeah, hopefully the midterm went well. Hopefully, you're a little bit less stressed now. I understand how stressful it can be, but hey, we're almost at the end of the course, so keep up the good work and we appreciate your hard work. So yeah, we're going to be talking tonight. It is nighttime. Some people ask what time I record these at. It's 12:45 a.m. right now, so not ideal. We're going to talk about binomial and geometric distributions, Hull's theorem, and relations. We're actually not talking about binomial and geometric distributions. It'll just be the last two, but so be it. It's tough teaching with a video camera because I can't show the blackboard and the screen at the same time. So we're going to go back and forth. The reason for that is Hull's theorem is a little bit hard to grasp at first. And it's not going to be much easier when I draw it out. But let G be a bipartite graph. You'll notice that there's like three parameters to G, X, Y, and E. X and Y are sets of vertices, and we're sort of giving the bipartition here. Like X is going to be all vertices of one color, Y will be all vertices of another color. So this is just a way of writing a bipartite graph. And we're going to define n sub G of S to be the set of vertices adjacent to vertices in S, where S is any set of vertices. That seems like a really chaotic right now. We'll draw out an example and kind of define it properly there. Finally, we turn to Hull's condition or Hull's theorem, which says that G contains a matching, we'll define what a matching is shortly, that saturates every vertex in X if and only if the cardinality of the neighbor set of S, I'm going to call this the neighbor set, is greater than or equal to the cardinality of S. And this must hold for all subsets of vertices of X. Again, quite chaotic. Let's go over to the blackboard and let's kind of draw this out. Okay, so there's a couple of things that we should go over before we completely look into Hull's theorem. First, we'll look at bipartite graphs. Then we'll discuss what a matching is. Then we'll discuss, we'll discuss matching, then we'll discuss what saturation means, and then finally we'll take a brief look at this condition right here. So, first let's talk about bipartite graphs. So some bipartite graphs that we've seen already include trees and basically any graph without an odd length cycle. We proved that back in recitation 10? Let's say 10. 10. So, those are the graphs we've been dealing with. But it turns out we can sort of like transform all of the graphs, or rather arrange our vertices in such a way that bipartite graphs will look like this, where we have one set of vertices on the left side and another set of vertices on the right side. So in this case, we'll call these vertices X and these Y. So this is what I meant by the partition. But a key thing to note about all of the vertices on the left side is that all vertices here are going to be the same color, right? But bipartite means we have some sort of coloring. So all of these vertices are the same color, and everything on the right-hand side is going to be the same color, which is just going to be the opposite color. So this is another way of drawing out bipartite graphs. So, okay, we've handled that part. Let's now discuss what a matching is. So a matching is said to be a set of edges in the graph with no shared endpoints. So if I look at this graph right here, I can kind of construct a matching. For example, that edge exists in my graph. So this is technically a matching because I have a set of edges, and of those edges, they don't share any common endpoints. Well, it's kind of trivially holds because there's no edges to compare it to. But maybe let's add another edge. Say this one, which also appears in the graph. This is also a matching. If I look at my two edges, no shared endpoints. So we're good. But if we were to add like this edge, for example, now we don't have a matching anymore because we have two edges that have a shared endpoint. So we'll remove that. So yeah, this is a matching. So we've defined that. Now let's talk about saturation. So saturation is a little bit tough to define, but in the lecture notes we define something called M-saturated, and this is a property of vertices. So the vertices incident to the edges of a matching M are said to be M-saturated. So if I were to give my vertices some names, then for this particular matching with these two edges, x1, x2, y2, and y3, wow, I'm too tired, they're going to be M-saturated. Because when I look at the edges of my matching, you know, we look at whatever it's incident to, and that's part of like the M-saturation. So when we look at this definition, G has a matching that saturates every vertex in X. In this case, our matching does not satisfy that condition, because we have a vertex in X that is not saturated by our matching. However, if we were to introduce this edge, for example, we still have a matching because edges don't share any same endpoints. But moreover, we have now saturated every vertex in X, right? Because all three vertices, you know, there's some edge going with them. Cool. So that's most of it. Now we're going to dive into this just a tiny, tiny bit. The proof for Hall's theorem is something that you can look up in the lecture notes. We're just going to make sense of it and leave the proof to later. So before we dive into like kind of parsing that and what it actually looks like in the graph, let's first, you know, figure out for sure what this n sub g of s is. So this is defined to be like the neighbor set for a set of vertices. So in this example, if we let s equal x1, x2, we want to determine what the neighbor set of s is in G. The way we do that is we take a look at our set S, consider one of the elements, say x, and we look, what are its neighbors? y1 is a neighbor, and y3 is a neighbor. So we'll include y1 and y3. Next, we'll look at the other element in S, x2. What are its neighbors? y1, well, we've already included that, and y2, which is not yet included. So that would be the neighbor set for x1, x2. Now, for Hall's theorem, we need that the neighbor set, the cardinality of the neighbor set, is greater than or equal to the cardinality of the set itself. So in this case, we do indeed have that the neighbor set of S is greater than or equal to the cardinality of S. But this has to hold for all subsets of vertices. We've just looked at one single subset. So I would also have to show for like x1, like if S equals the set of x1, then the neighbor set of S is going to be, I believe, y1, y3. And once again, we have that the neighbor set is greater than or equal to the cardinality of the set. If that holds for every single subset of vertices, then we have, you know, the backwards direction, since it's an if and only if. So if we have that, then we know that G has a matching that saturates every vertex in X. And in fact, you can try all 8 subsets of these vertices, and you'll see that it does always hold true, and we can get a matching that saturates every vertex. I kind of drew one before, but let's just draw another one. This is going to be a matching that saturates every vertex in X. So there you go, just kind of parsing through Hall's theorem. I didn't really have to do this, but it's for your benefit, so hopefully this is somewhat beneficial. Okay, let's go back to the screen. Oh, we're going to be talking about Hall's theorem more in just a minute, so don't miss it just yet. Okay, so now we're talking about relations. I do not like relations, but I will teach them to you because that is my job, and you will understand relations and you'll get problems correct about it, hopefully. If not, then, well, I guess it's my fault. So we're dealing with binary relations. And the binary relation is simply a set of ordered pairs. It is a set. Just take a moment to let that sink in. A binary relation is a set. Moreover, the set contains ordered pairs, and we have an example right here. This is an example of a relation. We have a set of ordered pairs. Hopefully me repeating that like 800 times is, solidifying it in your brain. But yeah, so if we take a particular element in R, this tells us that 1 is related to 2 by some relation R. I guess that is the relation we're looking at, and we denote it by 1R2. It's a little bit abstract because how do we have a name of a set, but it's also being used for this relation thing? I'll explain in just a moment. One last thing is that if we have a binary relation from a set A to B, then this is going to be a subset of A cross B, right? And this should make sense because we're looking at a set of ordered pairs. The first thing will come from A, second thing will come from B, and, we just want a subset of it, and that's what a relation is. Let's go back to the blackboard. So here's a toy example. Let's say we have a set A, which is 1, 2, 3, and B, which is a set 3, 4. And we have a relation R on the sets A and B. So R is forming a relation between elements of A to elements of B. Note that we can have A equal B. So we can form a relation when the two sets are the same thing. Just for this example, I decided against it, but it is possible to do that. A and B don't have to be different from one another. So here's an example R, which is a set of these ordered pairs, which are indeed first element from A, second element from B, and that holds for all of them. If we take a look at A cross B, that is every single pair that we could get, and indeed you'll see that R is a subset of A cross B. So this is a relation. R is a relation. That doesn't really mean too much unless we actually give it substance. And in fact, in this case, R is going to be the relation less than. We can always say that 1 is related to 3. That doesn't really mean too much. But in this case, R is actually this symbol. And if we check it out, 1 is less than 3. 1 is less than 4, and so on and so forth. This is the only item that was excluded because 3 is not less than 3. So you've seen relations before in day-to-day life. Less than is a relation, equality is a relation, inequality is a relation, basically all of your equalities, but there are other things you could do too. But I just wanted to show this because you shouldn't be afraid of relations. You've seen things like this in the past. But that's what a relation is. Let's talk about special types of relations. Back to the other board. Okay, so I lied. We're actually not going to talk about types of relations. We'll instead talk about properties of relations. So these are all adjectives for relations, meaning adjectives that can be used to describe a relation. A key thing to note here is that we're assuming for all of these cases that R is going to be a relation from set A to set A. So like I said before, A and B could be equal to each other. For the purposes of these definitions, that's the point. So we say a relation is reflexive if for every element in our set A, called X, the pair XX is in R. We say something is irreflexive if for every X in A, the pair x comma x is not in R. And note that has to hold for all x in A, not just some of them. Symmetry tells us that if we take two elements in A and the pair xy is in R, then that must mean that yx is in R, just swapping the order of them. Dude, it's so hard to make definitions fun, but whatever. Antisymmetric, the name is slightly deceiving. You would think it's sort of just does not imply, but this is the proper definition. For all x, y, and A, if we have both x comma y in R and y comma x in R, if both of those are present, then that must mean x and y are the same element. For transitivity, we say that for all x, y, and z in A, if x is related to y is related to z, then x is related to z. And as I mentioned before, anti-symmetric, the name is a little bit deceiving because symmetric and anti-symmetric are not opposites of one another. So it's good to just be familiar with all these definitions. I forget them all the time, but you should be a good student and memorize them and, you know, all that jazz. I think that's it for slides. We have one question today, so I get to go home and sleep. All right, so here's our question. Consider a normal 8x8 chessboard. In each row and each column, there are exactly n pieces where 0 is in between, n is in between 0 and 8, including 8. Prove that we can pick 8 pieces such that no two of them are in the same row or column. I will preface this entire problem by saying this is a hard problem. You are not expected to know how to solve this right away. And right now you're probably thinking to yourself, why are we talking about chess? I thought this was a graph theory class. Well, chess is awesome. But yeah, we are somehow going to change this question into something that we know. How we're going to do that is going to be kind of mind-blowing, and hopefully I can explain it well enough. So I just spent the past like 3 minutes drawing this out really, really nicely. So we're going to use it. Let's first get a visual understanding of what a board could look like. For the sake of convenience to me, I'm just going to let n equal 2, meaning I want 2 pieces in every single row and column, exactly 2. So let's kind of draw out what that could look like. So here is such an example where every single row has exactly 2 pieces, every single column has exactly 2 pieces. And this, if we prove this to be true, the question to be true, then it's saying that I can select 8 pieces from here such that no two of them are in the same row or same column. So let's see which 8 pieces I could select. Just to highlight how non-trivial this actually is, I just started coloring in some of these hoping that I would solve it. But you'll quickly realize that I can't just color however I want, meaning I can't just choose something that was not chosen previously, because when I do that, and I get to this row, I can't choose either one of these. And I need to choose exactly one, because it has to be in the same row or column, right? So anything above this, if I were to choose it, it would be in the same row as something else. So my last 2 pieces have to come from one of these 4. And in fact, one of them has to come from this row, and one of them has to come from this row. But I can't choose either one of these. So this current coloring isn't going to work. But this is just to highlight how difficult of a task this may be. So let's try to find a different one. So with a quick amendment, I was able to come up with this collection, and you'll actually note that the remaining 8 also satisfy the condition. But the point is it's not easy. So how are we going to solve this question? So here's one observation we can make. When I select a piece to include in my set of 8 pieces or whatever remaining pieces I choose, there are less squares that I can look at. Meaning if I choose this piece, then no piece can come from the rest of the row or the rest of the column. That is, a single piece will determine its own row or column. That is, like, it will correspond with a row and column. But more importantly, each piece will have a unique row and column pair. So let's take a look at this piece. Let's say it's in row 1, column 3. When I choose this one to include in my set, I am blocking off this one, which is 1, 6, and also this one. Like those 1, 6, and whatever this is, 6, 3. These pieces I cannot choose in my set of 8 pieces because I would be violating the same row or same column. And this makes sense because these two are shared, and those two are shared. Let's write out all of the pieces that we selected. Since we're selecting 8 pieces, and no 2 pieces can share the same row or same column, this means that each row will have its own unique piece, because we have 8 pieces and 8 rows. The only way we can satisfy it is if each row has 1 piece in it. Same thing for columns. Each column will have its own unique piece. So this one piece that we selected belongs to row 1 and column 3. And same with this one. It belongs to row 2 and column 6. And we'll note that I have 1, 2, 3, 4, 5, 6, 7, 8. So each row appears exactly once. And each column appears exactly once. 1, 2, 3, 4, 5, 6, 7, 8. I don't really know how to expand on this notion of belongingness without sort of giving you the answer. Hopefully what you're starting to see is that a single piece forms a connection between a row and a column. And more so, each row and column can have exactly one connection. This is probably becoming extremely confusing. So, what we'll do is actually represent this as a graph. If we were to have one vertex for each row and one vertex for each column, we can treat this as an edge, meaning we'll connect the vertex for row 1 with the vertex for R3. And what will happen when we draw out all of these edges? We'll do it in just a moment, but hopefully you're starting to guess what may happen. Let's actually draw it out. So when we draw out all of these edges, we have a bipartite graph, but these edges actually form a matching. More importantly, it's a perfect matching. Every vertex on this side, which we'll call X, is saturated. And interestingly, all of the vertices in Y are also saturated. This is because the cardinalities are equal to each other. This is just the collection of pieces that form what we want, but really we're starting out with a graph. And our graph should contain all of the pieces, and we're trying to find this matching. So we can draw in the other edges, but let's just do that actually. So this is the graph of that board, and I know this looks like something you would see in the Museum of Modern Art, but hey, I'm an artist, what can I say? So yeah, if we represent this board as a graph, or rather any board, we just consider the rows as vertices and columns as vertices, and we draw an edge anywhere there's a piece, then we have a graph, and our goal is to find a matching. Why do we want a matching? Because a matching will admit one edge to every single row and column, right? Every single row will have a unique edge corresponding to it, which means a unique piece corresponding to it. And we can't have more than one edge coming from a vertex because that would mean that, like, for example, if we chose 2 edges that came from R1, that would indicate choosing 2 pieces in the same row. So we need exactly 1, so we want a matching. So how do we determine, based off of these conditions, that we have a matching? Well, there's kind of only one way we know how to do it, which is by Hall's theorem. So let's try to prove this using Hall's theorem. So remember, Hall's theorem is a biconditional, but the backwards direction is more interesting to us, because if we show this to be true, then that would imply that our graph has a matching. Yeah, so that would give us a matching that saturates all vertices in X and moreover saturates all vertices in Y. So how are we going to do that? We're not going to go about considering every single subset of vertices of X. That would be a lot. That would be what, 256. I don't have all day here. It's already 1:35. So we need a quicker way of doing it. And on top of that, we would have to consider all board configurations, which would also not be fun. So one way we can prove this, like for all sets S, is we just consider an arbitrary set. And if we consider an arbitrary set and all of our work follows, meaning that all sets that we could have considered follows the logic that we present, then we're good to go. So we'll consider an arbitrary set A. So really there's two things that we kind of want to figure out. We'd really like to know what the cardinality of A is and what the cardinality of the neighbor set of A is. This isn't something we can actually easily do because A is arbitrary. The only thing I could say is that the cardinality of A is like less than or equal to 8, and the cardinality of the neighbor set of A is less than or equal to 8, but that doesn't immediately imply that. So we kind of need a different way of doing this. Instead, what is one property that we know about our graph? We know that for all vertices in X, the left-hand side, the degree of the vertex is going to be n, right? Each row has n pieces in it, which means there are exactly n edges emanating from each vertex. Why is that helpful? Well, if we consider the amount of edges going from A to the neighbor set of A, the amount of edges, well, each vertex is going to contribute n edges, and so there's cardinality A vertices. So in total, there are n times the cardinality of A edges going from A to n sub g of A. But now let's consider it from the opposite perspective. Right? We're counting like the same edges, right? Like we're still looking at a set of vertices and another set of vertices and being like, how many edges go between them? This, in the first way, we focused our attention on the left-hand side and looked at things emanating from there to get this value n times cardinality of A. Let's now focus our attention to the right-hand side and pretend we didn't know anything about A. Well, the neighbor set of A, we know that the neighbor set of A is going to be a subset of Y, which in this case are the columns. And once again, we know that every single column vertex has n edges emanating from it, right? Because, well, each column has exactly n pieces in it. However, does that imply that the amount of edges going from the neighbor set of A to A is that, just as before? No. And here's why. Before, we were easily able to say this because every single edge that emanated from a vertex in A was guaranteed to have its other vertex be in the neighbor set of A. Right? Like suppose we just looked at a couple of these vertices, maybe that's our set A, and we looked at every edge that comes out from it. And we look at the vertices that are in that grouping. So it would be these two, and then that goes there, and this one right here. Right? So all n times A of these edges have other endpoint of neighbor set of A. However, when we look at neighbor set of A to A, it's not guaranteed that those edges are going to go back to A. They could be this column edge, or like an edge coming from this column could go to some other vertex. For example, C5 right here. Sure, one of its edges does go back to a vertex in A, but there's also this one that goes to R8, which we didn't really consider in A. So in fact, the number of edges going back to A from n sub g of A is not exactly this, but rather at most that. At best, all of the edges do go back to A, but it could be less than that. It will never be more. So we've counted the edges in two separate ways. So overall, this would imply that the amount of edges is less than or equal to our bound. And if we divide both sides by n, and then just rotate this inequality, we get this. And this exactly matches our condition, our Hall's condition. And again, all this follows A was arbitrary. So I think that's it. I have to be completely honest. This is a really tough question. Thinking about the graph is kind of tough to do at first. But I think what you should get out of this is hopefully just a bit of intuition of how Hall's theorem works, how you would go about proving Hall's theorem. The entire transformation to a graph, you should not be too concerned if you don't understand that. It's a really difficult thing to do. But if you like finish this video, the one thing, or the couple of things that you definitely should understand is why this relationship makes sense, how the graph can be changed into how the board can be changed into a graph, and why we're looking for a matching. And secondly, all of this math, which is a little bit unintuitive counting the number of edges, but hey, we needed some sort of alternate way since the first approach didn't really give us a good enough bound. All right, it's like 1:45. I need to go home. So yeah, that's going to be it. I will see you in next week's recorded recitation. Yep, have a good rest of your day. Enjoy your weekend, etc., etc. Take care.